Uh, Hello to each and everyone. So this is example number 3. So this is what we are going to discuss today. And the main part of discussing this particular so-called this analysis is related to the plastic strain. So far, what we have done is in within the elastic limits. So today we will see an example of a plastic properties that we are going to apply for this particular example. So I'll just quickly let you know. So the example is related to the dog and dog bone specimen. So we are going to use the plastic material properties and trying to use the plane stress dog bone specimen. This is what we have to analyze. The Young's modulus and Poisson's ratio are given as below, and the width of the grips are like 1.5 times with respect to the middle of the width. So that's what we have to define it in our geometry definition, and this is what we have the plastic data. So make sure whenever we have any laboratory data in journal, they used to have like this in engineering strain and engineering stress. So initially we have to convert it into the two stress and strain data, and then we will try to compute the plastic strain, and that's what we will apply to our analysis. So just to make sure, here we will also learn it's not only about defining the plastic strain, but also to understand how Abaqus in general works. So let's say if our analysis get aborted, so it never means, not always means like it is due to some error. Sometimes it means like the defined properties are reached or the maximum peak values are already reached. So that's what we will see here quickly and understand. So as quickly as possible, we will start with the part. So we go here, and as a part module, we define our dog bone as a name. It's a 2D planar, deformable, and not wire because we are talking with 2D, so we define shell. So now we will define the geometry quickly. So it's going to start as 0, 0, and then we want it like 225 units long, 225 units long, and yeah, that's what we want right now. So the grid is smaller, but it's okay, it doesn't matter because the grid is normally a representation, and we want it like 75 uh, high. The length should be 75 high. So from here we can just simply say it is it's gonna be 225 comma 75, and then we have to define another horizontal length is going to be from here 175 comma 75. That's what we define it here, and that's it. Now we have to define this particular length, going to be 0 comma 50, which is the 1.5 times less than this one. Then we have to define the length here, and it's going to be 150 comma 50. And now we will define the edge, so we can use this center arc. We have to keep the center, and then we have to do endpoints. So let's say the center of radius will be 35. Then we define the, oops, sorry, it's wrong. We have to define it again here. So we define like here 150 comma 50. That's it. Now we define the center, and center we want it like 5. Sorry, center should be at 75. 175 comma, and it's going to be 150 comma 75. That's what the center will be. And now 2 points will be this one and this one. So that's how we define it in journal. Okay, so our CAD geometry is created, and this is what we have done so far. Now the next task is related to define the properties. So we already know this is, let's assume this as a steel part, we define. So this time we will not only define elastic, we'll define plastic. So first, since we know elastic, sorry, so where is it? We know already elastic. And since we are talking about isotropic, so it's called fine. We take percentage 0.3. So particularly for this case, we have to define plastic. So we have bundle of plasticity models, but today we will take only the simple plastic one. So here we have to define the yield stress in plastic strain. So what I did, I just did a conversion of data, and here it is. So we can just take these values. So what we did, like we took the engineering strain from percentage to the actual values. Then we calculated to stress and strain, and from that particular, we try to calculate our plastic strain. So then, since it is true stress, so we have to put it in the yield stress value. And for the plastic strain, these are the strain values that's going to activate. That's it. So we just apply this condition here. And now the next part is to define our section. So we go to the section again. We say this as like dot bone. And again, we are taking a solid and homogeneous part. We continue it. Still is already defined. And the thickness in the it's not given in journal, so it's all up to us whether we want unit thickness or anything else. So we will take by default unit thickness. Perfect. So now is a assignment section assignment. So we have to select the reason. This is what our reason is. We assign it. This is what we have as a job bone. Perfect. All fine. Now the next step is assembly. Since we have only one part, so it's not going to be a big issue. Okay, we have defined it. Now it comes a loading condition. So when it comes to loading condition, we have to define the load as well as the boundary condition. So if we see this particular problem, so here we are applying a constant, or let's say a pressure of 2000 MPa. That's what we have to apply to this part. Make sure like we have make a symmetric of it. So here we will apply the symmetric boundary condition across y and across x. That will be our initial boundary condition. So let's go and define first initial boundary condition. So, or rather than symmetric boundary condition, which is symmetric BC1. So symmetric boundary condition is applied to initial, all fine, and it is already selected here, symmetric. We go here and we select this one is going to be for the x symmetric. So we select here and we have an x symmetric. So it's going to be the same to the other side also. And we click OK, and then we define again. It's going to be the symmetric BC2 for initial case, symmetric, perfect, and it's going to be for the y direction. So it's going to be y symmetric. That's it. Perfect. So these are applied. So we have to apply a load boundary condition. So we will say apply load. It's not going to be on initial, rather than we have to create a step. So since we forgot about it, we go to the step and we go to the apply load, and it's going to be a static journal, all okay to us. And here we have to understand this is going to be nonlinear analysis. So geometry is going to be nonlinear. We have to click it on. Now incrementation, this time we are going to change a bit. So we don't want like, so this actually section is all about how much percentage of load is going to apply to our geometry. So if it is 1, it's written here, which means all the 2000 MPa, whatever the defined load we have, is going to apply in a single shot. That's not what we want. We want it to be gradually applied, unless it will show an error. So we want like, let's say 0.1. It means like the 10 percentage of the load is going to apply at a first step, and then as a successive steps is going to apply later. So that's what exactly we have to do. Is we have defined it 0.1. So that's it, and it's all okay. Now again, I forgot to give the step, but right now I have done it. So we again go to the load condition. Our boundary conditions are already set. We have to go to the load boundary condition. So load, so we say apply load. It's now the step is here as apply load. We give the pressure here, and we continue, and this is the part where we have to give it. And how much magnitude is given, like it's 2000 MPa, so we just define 2000. and perfect. So it is in this direction, but should be reversed. So we again go to the load condition, double click here, and try to give a negative sign here, and that is good enough. Perfect. So yeah, now we have to do the mesh, and since we already know about mesh, so if you try to click here, seed part instance. So if you just do it here, let's make it for a part. So it's going to have a global size from its own size. If you apply here and if you try to mesh it, you will see this particular mesh is not so much good and the results are not going to be that much good enough. So what we will do, we will try to uh, remesh it and check it out like how good we can do. So let's say I just wanted like 2 in journal and now I apply here. I delete my older mesh and I guess it's going to be really fine right now. It's going to take some time. I guess right now it's good. It's a good mesh. So if you want, you can further reduce it to make it more uniform. And now the important part is we have to define our element type. Try to understand we are here to define the plane stress. So the family is going to be the plane stress family. So plane stress is already selected. We are looking for linear and it's all up to us whether we want reduced integration or full integration. So let's go with the full integration and the linear order, like the first order, and let's check it out how it goes on. So this is what we have defined. So all we have to do is to run the simulation. Now what will happen is like we will see like with the one mysis stress as a post-processing part and try to understand like how it goes on. So let's say we submit the job and it is like job on and just continue. Okay, I'm fine. Now we submit it. We submit this part and we'll check it out like how this analysis is going to predict the results. So make sure like here the plastic strain is given. I mean, it's not a dynamic analysis, it's still a static analysis. But the only thing is like what we have defined is the nonlinear material. So if we talk about like nonlinearities and one of the nonlinearities defined here. So it's running, we can monitor it. So as we can see like it gets aborted. So we have to check it out how, why, what exactly is the reason behind of the abortion. So it says like time increment required is less than the minimum specified, correct? So it gets stopped at 0.27, which means at 27% of our total applied pressure, it gets stopped. And we have to understand why it gets stopped. So which means the first is like the time increment required is less than the minimum specified. So what we can do, we can reduce the time increment from 1e to the power minus 5 to 1e to minus 10 and then try to check it out again. But the point is like it doesn't make much more sense if we do it right now here incrementation. If we make it 10, then let's check it out how it works. I just rerun it. I just submit it. Okay, and then we will understand whether it again provides the same error or not. So once we it starts running, we can also understand one more thing, that is unsuccessful attempts given by the Abaqus solver. Make sure like whenever we have this one u, which means like system has given a particular time step to it. Let's say we define, if you remember, we defined earlier like 0.1 time step, but unfortunately at that particular time step, initial was all okay, like hold on, it's just running, trying to get to 1e minus 10. Okay, seems like taking a bit of time, but So whenever you see one U here, so it is an unsuccessful attempt by the solver. So again, as we can see at 1 E minus 10, again it aborted and it needs a less uh, increment time. So what exactly is happening? Let's say whenever the solver tries to check the equilibrium condition, let's say at 10% of the load, it works, it gives us the answer, it's perfect. Now again, it tries to achieve the same for 0.2 and it works for it. But when we see one U, which means like it is not able to converge. So whatsoever we see the total iteration, so here we see the iterative methods that is applied by the Abaqus, let's say Newton-Raphson method, and it's not able to converge the answer. So what it tries to do, it tries to reduce the time step, reduce the amount of load. This was like 10%, 10%. Then it starts reducing the, it's like almost zero point 0, like the 3% of load strength. And then again, it was able to converge it. Then this is how like all the process goes on and on. So it's really important, like whether what exactly this abortion means here. So what we have to do is we have to check now our analysis, whether it is right or wrong. So we just go to the results, and now we define here, this is what exactly our analysis is. So if you try to understand, then this is what happened to us. So initially it starts stretching, then after that it doesn't stretch it out. And the reason is, if you remember, the peak stress that we have defined in our model was 930. Let me show you. The plastic strain that we have defined was 891 here, correct? So if this value is reached, which means a defined peak value of our system here, and if we see the visualization is, it's 891, correct? Almost 891. So the elements are not able to, I mean, they don't have enough, I mean, the defined stress is not enough so that they can surpass it. So they have a limiting value, and after that limiting value, they are not going to have much more stress than what we have defined. So which means uh, we might think like our analysis get aborted, but in journal, it's not going to go even ahead of it. It's always going to abort, which means like at 27 percentage of, let's say 27 percentage of our load that we have applied here, it's only, and we have defined a maximum peak stress of 891. It's not going to surpass it. So that's why at 27 percentage of stress, I got an equilibrium state. So it's not going to increase a bit more also. So that's where we have to understand like each and everything, that whatever we have defined is what we get. So this analysis is all okay, everything is all fine, and we don't need any other iteration for it. So what we can do is we can go to the ODB file, ODB field output, and we can define our let's say the stress, let's say one mysis stress on a particular, let's say on a node, or we can select it from the node here itself or an element, and we can try to plot it. So as we can see, like it is just going at 27 percentage, or let's say at 0.27, it is going to 891, and after that it's not going to perform any analysis. And it is true also, it's not going to perform since it has a maximum peak stress. So we already know like the yielding has already occurred, and we can define the softening as well as the damage behavior. So if we define the damage behavior, it's trying to get broken in two pieces in general. But as an engineering point of view, we already know like the material got failed at this point, because this is the maximum yield stress that we have defined here. And after the more we define, we can either get the wrong results, because like what we have defined is a load boundary condition. If we define the displacement boundary condition, it will not follow up that yield stress, it will try to stretch it. And that's where like we understand that's the wrong analysis, it's meaningless. So whatever we get it here is good enough and within our reach or within our limit that we have defined. So this is all about the plastic strain, and we will see some other analysis also soon after some time in the next probably video.